the gradient formula that is going to work with the x squared function, whenever you wanted to find the gradient, you are going to realize that you need the gradient formula for that specific given function. So for f of x is equal to x squared, the derivative of it is 2x. That's the difference quotient. That's the derivative. So which simply means when x is equals to 2, my gradient formula is what? 2x. So my gradient at that point is equals to 2. Where there is x, I put 2, then my gradient is 4. Are we together? So the process that we have done so far, this whole process that we have done, it's called the first principle of differentiation. This is what we call differentiation. So that's what we call differentiation. So differentiation actually is a process of finding the gradient quotient for every given function. So we have done that using what we call this one, we call it the first principle. This is the first principle. Are we together? So according to the Namibian syllabus, when they say differentiate, they don't want you to use the first principle. Are we together? They want you to use the first product rule, they want you to use the power rule, they want you to use chain rule, depending on what function you are given. But all of those rules that are rules of differentiation you are going to learn, they are all products of the first principle. Because what we call the power rule, let's talk about the power rule. The power rule of differentiation. I'm going to say, I want you to realize this. Let's say I'm going to give you power rule states that if we are given y is equal to x raised to n, then the dy on dx is equals to x is equals to n x raised to n minus 1. Okay, let's come a little bit and explain this part, because some of you doesn't know what it means. The dy on dx. Instead of writing the difference quotient, we are saying, if you look carefully, what we have divided here, let's go a little bit up, was rise over run, which simply means if we are to look on the zoomed point of x, the point at A, where the triangle fits inside the point itself, right? You are going to realize that your rise is also becoming small. That's what we call the delta of y value, which means the smallest value of y is divided by the smallest value of x. Your run, which was your x, which was approaching 0, is becoming small. So every value of x, when you are using the first principle to find the exact gradient at the exact point, which means it's going also to become the delta x. So the x value of y is becoming small as well. So that's what we call the dy on dx. So simply means difference of quotients or the gradient at the exact point. So if you look in your books, you're going to realize that there is the Lagrange notation and the Leibniz notation. The Lagrange notation, it says dy on dx, and the Leibniz notation, sometimes it says you are only allowed to use dy on dx if the function was given in terms of y. But if the function is given in terms of x, of f of x, like f of x is equals to x raised to n, you can't come down and say dy on dx. So that's when you are now using the what we call the f prime of x. So this dash represents the same thing, the difference quotient at the end of the day. So that's where you use what we call the Leibniz notation. So Leibniz give us this notation. If our function is given in terms of f of x, we can use f dash of x, or we call it the f prime of x. And if our function is given in terms of y, we use the Lagrange notation, which says the dy of dx will be our derivative or our gradient formula. So we said it's either derivative or the gradient formula, or we are dealing with difference, quotient. All of these are the same thing. Are we together? So do you realize that we were given y is equals to x squared, and the dy on dx was equals to 2x. You see that? If you look careful, we get this 2x by the first principle. So I'm going to use the first principle again on this. Let's use this. If f of x is equals to x cubed, what will be the f prime of x? So by the first principle, let's go. We said the f prime of x by the first principle is equals to the limit h approaches 0, where we have f of x plus h minus f of x all over h. Is that so? So in this particular moment, our y, which is our f of x is cubed, which means our y here is going to be cubed. So that's going to be the limit h approaches 0 is going to be x plus h cubed. Are we together? Minus f of x. What is our f of x? Is x cubed. Are we together? It's all over h. And we know that since we have done x squared, right? We have done actually x plus h squared, and we said it's equal to x squared plus 2x plus x squared. So which means x plus h cubed will be the x plus h multiplying x squared plus 2xh plus h squared. Is that so? And that will give us this times this, we are going to have x cubed. This times this, we are going to have 2x squared h. This times this, we are going to have xh squared. And this times this, we are going to have x squared h. This times this, we are going to have 2xh squared. This times this, we are going to have positive x cubed. So if I add these together, I'm going to have x cubed plus 3x squared h plus 3xh squared plus h cubed. Is that so? So that's what I'm going to write as our limit h approaches 0. We're going to have x cubed plus 3xh squared, right? Plus that's correct. That was 3x squared here. This h is not squared, and then plus 3xh squared plus h cubed minus x cubed all over h. So that's it. I'm going to check this one out. So which means as the limit h approaches 0, we are going to realize that this and this will cancel, right? And if I factor out h on top, I'm going to have h, and then we'll be left with 3x squared, right? And then plus 3x h plus h squared over h. So this h and this h cancel. So now there is no h on the denominator, which means there is nothing to fear. Our h can be 0. But remember, if our h becomes 0, this and this will disappear. There will be zeros. I will be left with 3x squared. That's all. Now, remember, we have 3x and our h is 0. It's like 3 times x, it's 3x. 3x times 0, it's 0. You get it, good. So look careful. Look careful. This simply means now, if we look careful, we were having, let's analyze, we want to analyze the first principle, the results of the first principle. This is what gives birth to what we call power. At first, we were having y is equals to x squared, and our dy on dx was equals to 2x. And now we were having f of x is equals to x cubed, and our f prime of x is equal to 3x squared, which simply means we can go to this result straight without the first principle, because it simply means this 2 was the index. Look, this 3 was also the index, and they multiply this x. When it applies x, they reduce the index, reduce itself by 1 every time. That's why you see our x, 2x is raised to 1 now. It was 2. Our x is now raised to 2 instead of 3. Yes. Yes. So which means our power rule is the shortcut of the first principle. So we can differentiate using power rule instead of the first principle. That's why the Namibian curriculum doesn't allow its students to use the first principle. They said just use the what? The power rule, which says y is equals to x raised to n. So d1 on dx is equals to n, which is the index, will come down and multiply, and our n here will subtract itself by 1. This is our power rule. So now let's try to use the power rule, given that y is equals to x squared minus 4x. Find the dy on dx. What will you do? You are going just to say dy on dx is equal to, remember our 2x, then the 2 subtract 1, then you just the 2x minus, here our x, yes, our x is raised to 1, so if 1 comes down to multiply 4, it will remain 4, and if we subtract 1 from the index, it will be x raised to 0, and by laws of indices, anything that is raised to 0 is equal to 1, so our x raised to 0 becomes 1, so 1 times 4, it will remain 4, so our dy on dx is 2x minus 4, that's our derivative for that formula.